Okay, so welcome back. I feel like we just heard so many amazing, just unbelievable information and heard resuspension come up, risks, things we can do, which I think segues nicely into our session 4 topic. And I would like to introduce our moderator for session 4, Pooja Ramaswamy. I'm going to provide you some information on her background. So for a decade, Pooja's professional experience in interior design and design strategy applied to transit environments, hospitality, and workplace interiors has supported strategic transformation. In her current role as a design strategist at Metrolinx, she leans on her strengths of storytelling and strategic thinking to provide guidance on the design of customer-facing physical touch points in new transit environments shaping the city. Through developing design guidelines, conducting ongoing design reviews of capital projects, and facilitating dialogue between stakeholders across the organization, she ensures the needs of all customers are responded to thoughtfully and inclusively while aligning with organizational objectives. In her role as senior designer at HOK, she worked in interdisciplinary teams to design hotel and workplace interiors for global clients in Canada, US, and the Middle East. Pooja received her Bachelor of Interior Design at Toronto Metropolitan University. Alongside her professional role, she is currently a part-time MBA candidate at the Rotman School of Management, where she continues to augment her expertise with economic innovation and foresight to advocate for strategic and inclusive design thinking and global leadership. Thank you so much for joining us, Pooja. I will now hand the screen over to you.
Thank you so much, Lois, for that introduction. Hello, everyone. My name is Pooja. I am very excited to be here today, and let's jump right into session 4. Indoor environments are designed to support work, life, and education, among many program types which were shut down during the pandemic. Upon reopening, guidelines were developed to implement safety protocols, yet yearly cold and flu seasons require similar attention. This session looks at scenarios whereby infectious particles can be transmitted in indoor environments through air and surfaces, and how interior designers can develop a guide specific to interiors for mitigating viral transmission. The 2 speakers contributing to this session are Dr. Andrea Ferro, professor in the Department of Civil and Environmental Engineering, and Ms. Janine Glazier, architect and senior project manager at the University of Wisconsin-Madison. Before I introduce our first speaker, I'd just like to encourage everyone in the audience to throw their questions up in the Zoom Q&A function. We will have a Q&A after the 2 speakers' presentations. Okay, so presenting first is Dr. Andrea Ferro, professor in the Department of Civil and Environmental Engineering and Associate Director for Research Engineering in the Institute for a Sustainable Environment at Clarkson University in Potsdam, New York. She is a registered professional environmental engineer in the state of Massachusetts. Dr. Ferro's technical expertise is in indoor air quality and human exposure to particulate pollutants using direct measurement as well as mechanistic and stochastic models. The overall goal of her work is to improve human health by improving air quality through source control, ventilation and purification strategies, education, and regulatory policy. Her current projects include characterizing of respiratory aerosol emissions from humans, virus resuspension, and aerosol transport in indoor environments. Dr. Ferro, thank you so much for being here. The floor is yours. Dr. Ferro, let me see if you are up here in Zoom.
I think I got it now. I was a participant, but now I can present. There we go. Pooja, thank you so much for the introduction, and thank you to the organizers for including me in this important symposium. I'm thrilled to share this with Janine, we met a few times in preparation for this, and I've already learned so much from her. Many of you have seen this already. So this is a nice image of short-range transmission of respiratory viruses, where we have the infected person with the aerosol coming out of their mouth and the receiver here. And that we have the aerosol, which is the particles that are suspended in the air that are 100 microns and smaller, and then these larger droplets that can fall quickly onto the fomites surfaces. So my work has to do with what happens when those particles are on the fomite, and that's what I'll talk about today. Actually, in my lab, we've done quite a bit of work on the emission of the aerosol. So we found that not only is loudness a major factor for the emission rate of the particles that are emitted during these different vocalization exercises, but also frequency. And recently we published a paper to show that that children's emissions are about 5 times lower than those for adults. We've also done quite a bit of work on what happens to the aerosol once it is emitted from a person and how it moves throughout the room. And you've seen some of those images as well in discussions over the symposium over the last day. This shows that the aerosol is sort of well mixed throughout the room. It's that's often how we model the exposure of another person that's in the room. We often assume that that once that the aerosol gets out from the person's mouth, then it mixes throughout the room. And then today I'm going to be focused mostly on what happens after those particles deposit onto surfaces and get resuspended up into the air. So this shows the little arrows being fairly small. If a person is walking and moving, and resuspending those particles, they're also helping mix them throughout the room. So we know that the particles that are resuspended from surfaces can get throughout the room, and as Dr. Lee showed, end up in the ventilation system. So just a definition of resuspension: if we have particles that are in the air, they will deposit eventually on surfaces or be removed from the air with the ventilation. But there could be an external force applied to those particles that removes them. So the particles have adhesive forces that keep them on the surfaces, but an external force, even a foot stepping down, creates enough of external force to detach those particles. The larger particles are easier to detach than the smaller ones, just because of the balance of forces. So that's something that we'll see today as well. This is a nice image from Jordan Petch's group, so that the accumulation of bioaerosols indoors. So now we're talking generally about bioaerosols. So this could be fungi or bacteria, also viruses, that there are some that are outdoors that are going to come in with ventilation and infiltration, and then mix throughout the room. And you also have the ventilation going out, right? So we're moving the particles that are in the air, the bioaerosols that are in the air. You can have growth of some, and that, is mostly related to the fungi. Also, the pets can track them in. The pets can be sources themselves. Here's the person, I adapted this, stealing that emission of the respiratory aerosol. But here's what we're going to focus mostly on for this session, or at least my part of this session, is those particles that then deposit and then get resuspended up into the air. So there's this cycle of deposition resuspension that occurs with human activity. Interestingly, the HVAC system can produce that external force. You have some airflow that's produced by ventilation systems, but it's typically not high enough to induce resuspension. This is just a summary of the ways that bioaerosols can accumulate indoors. So the things on the left add to the bioaerosols: natural and mechanical ventilation, infiltration through cracks in the building envelope, and then indoor emissions. So there are all these indoor sources: humans, pets, potentially plumbing, resuspension, and so on. And then for removal, we have deposition onto indoor sources, but now we know that that's sort of, the particles do deposit, but some of them may resuspend again. Filtration, we've talked about filtration over the last day as well, and ventilation out. So many people wonder how big of a source this is for resuspension. The data I'm showing you here are estimated emission rates in mass per time. And so there are many indoor sources that have been evaluated: vacuuming, frying, candle burning, smoking. These are large indoor sources of particles. Different studies for walking, resuspension from walking, have shown various levels of emission rates for human walking, but also these studies have different particle sizes, and we know that the larger particles are easier to resuspend, and you're going to have more of those. So this study, which shows walking as a source that's sort of in the same range as these other major indoor sources, was for larger particle sizes, 0.8 to 10 microns. These are for smaller sizes. So it is a major indoor source. And in fact, it can be the main source of indoor particles if you're missing those other major sources, right? So if there's no combustion sources happening or other sources of indoor particles, it can be the main source. So these are data that were collected by Mar Viana in Barcelona in a hospital. And you can see that so basically what this is showing is daily increases. So this is over a long period of time, several months. And you can see that these peaks in particulate matter, so this is PM 2.5, the airborne particles that are 2.5 microns or less, are, increase every day. And that's associated with the activity that's happening in the hospital. This is an oncology unit. These higher peaks are associated with cleaning activities. We also know that resuspension is an important route for in indoor spaces for bacteria and fungi. So these are data collected. This is from Jordan Petch's group at Yale about 10 years ago, did a study in a classroom and showed, and in this case, I'm showing you for each of these plots, we have the particle mass. So this is the mass of the particles per volume of air in different sizes. So that's the x-axis is the particle diameter. And you can see it's normalized by the size of the size bin. But you can see that for particles, when the space is occupied, this is the solid line, the concentrations are much higher, and most of the concentrations really are the larger particles, the 10 micron and below is where most of the particle mass is. There's still quite a bit below 10 microns as well. When it's vacant, you can see with this dashed line that it's much lower concentrations. This outdoor, there's not much of a difference between when the classroom was occupied and vacant, which it shouldn't be because the outdoor isn't associated with what's happening in the classroom. But if you look at the bacterial genome, that's also the case. Without people in the room, you have this very low concentration. And when it's occupied, much higher. You can see that the peak here is a little higher, like 3 to 5 micron size. And outdoor, there was actually a little bit more during the occupied as well. We're really focused on this indoor space, and we know that really there were no other sources, that resuspension was the main source of that increase in concentration. So I myself have performed many studies on resuspension, and others have as well. And these studies have occurred in homes, schools, hospitals, other types of buildings, but also in laboratories so that we can control the different factors the major factor is just the way people walk can be a major factor, because the forces that, and the kinds of shoes that they're wearing. Also different factors have been tested with various studies: the type of particle, the flooring type, the floor dust loading, the relative humidity, which is also related to the electrostatic charge, shoe type, and individual walking style. For this symposium, I think I highlighted these because I think that these are things that we can think about in terms of interior design, right? Certainly the flooring type, but also the floor dust loading has to do with how you can clean those, the flooring and other surfaces. And then the others have to do with how you operate the building. For most of these studies, what we do is measure the concentration of the particles over time. And so in this case, what I'm showing you is the particle concentration this time in terms of number of particles per volume of air. And you can see that the background is quite low. So before this resuspension event, there would be background is quite low. There's not many particles in the air. And then there's a resuspension event. In this case, it was just a couple of minutes. And you can see the concentrations increase for particles of different sizes. We started at 0.4 to 0.5 microns all the way to 10. And I think Shelley Miller talked yesterday about the different sizes of particles. 10 microns and below are what are called inhalable, so that they can get into the respiratory system. And then different size particles will dictate sort of where they end up in the system, in your respiratory system when you breathe them. It also is really very important for resuspension. Again, the larger particles in the size range being easier to resuspend. These data are taken from a mechanical foot that I borrowed from the Lawrence Berkeley National Lab. And so we were able to very much control these other factors and look just at, in this case, we were looking at flooring. I just wanted to show you some other results. This is from Brandon Bohr's lab, where they're looking at not just particle concentrations, but also biological aerosol particles. And so the figure I just showed you is more like what's happening at the bottom here: low background concentration, then there's a resuspension event. In this case, theirs was about 20 minutes, and then a decay. And you can see that it doesn't decay right away, right? These are smaller particles that are up in the air, and they take hours to deposit. And so you're going to have an elevated concentration for some time. And this is Dr. Prather, Kim Prather was talking about this yesterday, right? You can leave the room, the person who's emitting the virus into the air can leave the room, but it's still elevated, the concentration in the room. Okay, so the plot just above it is talking about the total particles. And so what this is showing you is that this is the size. So we're at 0.4 up to 16 microns. You can see that most of the particles are in this sort of 3 to 5 micron range. And then for the one above, this is going to be the fluorescent biological aerosol particles. So this is getting a sense of how many of those particles are biological. And you can see also an elevation in the particles in that size range. They also looked at a baby crawling. I love this one, so had to show you. Same thing. You can see that actually with the baby crawling, this is a robotic infant. You do get an increase in concentration, and then the decay, and still high elevation during the resuspension period and tapering off. Okay, so I mentioned that we were looking for that for the one study, actually several studies looking at flooring. So this is definitely relevant to the interior design. And so what this is showing is the resuspension fraction on the y-axis. So this is the fraction of particles that are on the surface that get resuspended, right? So these are the per footstep in this case. So it's per event. So if you have, 10 to the -3, for example, that's 1 in 1,000 particles that's on that surface gets resuspended per footstep, right? So what this is showing is for the particles that are less than 1 micron, and we looked at carpet, three types of carpet: high density carpet, low density carpet, and looped carpet. So the high density and low density carpet were cut pile, and then the loop pile is the green, and then hardwood and vinyl flooring. For these smaller particles, it didn't quite matter. There was no statistically significant difference between the resuspension fraction for those types of flooring surfaces. But for the larger particles, it did matter. And if you look at these two largest sizes, so 3 microns to 10 microns, the carpet, especially the low density carpet, was about 10 times, had about 10 times higher resuspension fraction than the hardwood and vinyl flooring, right? And so there was all these differences. So between the high density carpet and the low density carpet, the low density cut pile carpet had the highest resuspension fraction, followed by the high density cut pile, followed by the level loop pile, and then the hardwood and vinyl were the smallest. So, so just to summarize there, in this case, if you're looking at particle resuspension, you have the same amount of particles, the same loading of particles on that surface. The best choice would be a hard surface, and then the worst choice, a cut pile, low density carpet. But there's more to the story, and that is if you look at how much dust is on surfaces for flooring surfaces in different environments, you'll find that carpet actually, just because it's harder to clean and remove those particles, that the dust does build up more than on hard flooring. So these are data. So this is the geometric mean and the 95th percentile for carpet and hard floor for studies that were done in the field, one by Adge et al. Many years ago. We followed up with a similar study, but not as extensive, about 10 years ago. And there have been more recent studies too. So that you can see that if you compare carpet with hard floor, there's the dust loadings are about 10 times higher for carpet. So now you have resuspension fractions that are higher for carpet, as well as the dust loading tends to build up on carpets. So this could be resolved with cleaning, but these are data from the field. So let's shift and talk about viruses. This is a few of the summary statements by Dr. Prather, who spoke yesterday at the symposium. That the role of resuspended virus-contaminated dust and particulates is an open question, and so that we need to study this. So following this, I worked with Lindsay Marr and Jordan Petchia to get sort of a rough, sort of back of the envelope calculation on what we think, because we do have estimates, models for resuspension. And so looking at the size of the particles that are carrying the virus, the respiratory particles, can we estimate what would be this source? And we estimated with many assumptions that the resuspension source is about 1/100th that of direct emission. That is, if a person is emitting the virus in the room, right, for some period of time, and then another person comes in, or that person walks in that room, what would be the emission? And so it ends up, the calculation that we did, it was about 1/100. Again, there are lots of assumptions in here, and it wouldn't matter what the ventilation rate is, the size of the room, all those things. Should we worry about resuspension for viruses? Of course, it depends on how long that virus, the infectivity of that virus. And so these are some estimates on the inactivation of SARS-CoV-2, and we can see that the half-life is about at least an hour in aerosols, and also a lot longer on surfaces, up to days. So we do know that we have viable virus on these surfaces. We conducted a full-scale experimental study using influenza A. as our virus. So this is the first full-scale experimental study on virus resuspension, at least to my knowledge. That was just published a few months ago. So we did our experiments in a biosafety level 2 laboratory at Trudeau Institute in Saranac Lake. It's an infectious disease institute. And we had a full laboratory. I'm just going to walk you through this a little bit for the experiments. We would enter through the door. There was plastic sheeting here for the person to get to doff, put on their clothes. And, so we had them wearing a Tyvek suit, the person who was doing the resuspension activity. We emitted, this is a nebulizer. So we emitted the influenza virus in a suspension out into the laboratory, and then waited for several hours for it to deposit. And then we had a person come in and walk within the laboratory to resuspend that. We were collecting samples on the surfaces. So there were open plates where we were collecting samples and analyzing those. And we also had impinger samples so that we were pulling the air and then collecting the virus with those impingers. We had a couple of just particulate matter monitors as well, aerosol instruments to measure the concentration of the particles in the air during the time, and we measured in multiple locations. This is what it looked like. So we had to cover the surfaces with plastic based on our biosafety protocol. And here's where we emitted the virus. Here it shows you where the location of a couple of the impingers and our aerosol. This is a aerodynamic particle sizer. So the particulate matter concentrations, what this shows you is here's the particle mass in milligrams per meter cubed of air. So milligrams of particles per meter cubed of air. And this is for particles that are 20 microns and below, which is what the top of what this instrument measures. And so you can see the background was low again. And during the emission, the nebulizer, the concentration goes way up. And then it decreases over time. So it takes several hours to get back close to the background. And then there's a resuspension event. So this is the walking. You can see the particle concentration goes up again and then decreases. So that is what the time series looks like. That's for the particulate matter. But if you look at the virus concentration, again, we collected them in impingers. You can see during the initial emission, most of that, the virus was closer. These locations are close to the nebulizer, and these are further toward the end of the room. So there wasn't, during the source itself, there were higher concentrations near the source, which is expected. But during the resuspension, the opposite was true. Most of the virus was toward the other, that was resuspended was toward the other end of the room. And that is because where the nebulizer was, there was a cart and there were other things that were in the way. So most of the resuspension activity took place on the far end of the room. So that also makes sense. As a summary for this study, we looked at, so this is the initial emission for clean surfaces. We cleaned all the surfaces first, and then resuspension source. So this is the viral copies that were in the air, right, per volume of air. And so we can see it's about 100 times less during that resuspension event than the initial emission. We had fairly low air changes, below one air change per hour in this room. So much of the virus that was emitted ended up on surfaces. And that was the source of that. We actually looked at dusty surfaces because, as I mentioned, the size of the particle makes a big difference for resuspension. So we were thinking that, okay, if most surfaces in real environments have dust on them, and the dust could act as a carrier for the virus, right? So if the viral liquid particle falls on a dust particle, then it might be easier to resuspend. We did see a slight elevation in the resuspension with the dusty surface, but very, very small, but there was some. I also wanted to mention clothing, right? So we talked about clothing and also other surfaces. So this is a study that was just published by Dusan Lucena and Brandon Bohr on comparing particles released from clothing and skin. And that here is shown by someone seated and doing seated activities compared to walking, compared to vacuuming and cooking. And so this is the concentration, the mass concentration by particle size in the breathing zone of the person. And then you can see the different sizes here. So this is similar to the other plots I showed you. So you can see that compared to vacuuming and cooking, the walking and seated activities were lower concentrations, and much of that concentration was in the larger sizes, which one would expect. The walking had higher concentrations than the seated activities. Other studies have shown that walking actually in the Dusan Lucena was involved in these studies too, where you have the walking is about, if you look at all the particles that are emitted, about 2 times more emissions than seated activities. That was for just another study in certain conditions. So we do see higher emissions from walking compared to release from clothing and skin, but the clothing and skin is still substantial. But here's the difference. The intake fraction is higher for the seated activities. So this is a person, this is in their breathing zone, and the emissions are from their clothing and skin, which is closer to their breathing zone than the floor. And also they're seated, and so there is going to be, they're not sort of walking away from the source, which you do when you're walking. So there's inhalation intake fraction is higher for the seated activities. So I think that this shows that resuspension or from clothing or skin or shedding is also important. There's some evidence of this from the field. This is early data from the Fankang Hospital in Wuhan, and showed that, that there was the SARS-CoV-2 RNA concentrations were fairly high in the protective apparel removal room, even though there were no patients there. It's shown here too. So that's more support. So let me summarize here. Hopefully I haven't taken too long. The viruses can resuspend after settling on surfaces. This was predicted by models and also by full-scale measurements. That particle resuspension could be an important exposure pathway. So I showed you sort of this round number of the emission being about 1/100th of that of the direct emission, so from resuspension. But you can imagine scenarios, say you had 100 people in a room, right, a classroom, that's 100 times the emission. And so you could have different scenarios. Say your ventilation rate was higher or lower, that would change that equation. I think that the takeaway here is that it's important to have surfaces that can be cleaned, and so we can reduce that reservoir of pathogens on surfaces. Also, that we do need to look at particle release from clothing, which could be more important for exposure. And also, just to go back to these other engineering controls that we've discussed, we've got, so ventilation would, filtration, disinfection would certainly reduce the exposure by reducing the concentrations of the particles that are resuspended. And just to tie into Janine's talk, when we look at engineering controls with the hierarchy of controls, and this is this hierarchy is long before SARS-CoV-2 arrived on the scene, that we know that these engineering controls can be quite effective, especially compared to PPE. This is in general environments. We know that, for reasons of people not wearing the PPE properly or other other reasons that engineering controls, we have a better control of that and of the source. Okay, so that's it for me, and I will stop sharing.
Okay, thank you so much, Dr. Ferro, for that incredible sharing all of that incredible work with our audience. I mean, to me personally, it's fascinating to understand how the experiments that you conducted, concluded to those findings. It's pretty incredible. I would now like to invite Ms. Janine Glazier to join us for the second presentation. Ms. Glazier is a licensed architect and senior project manager working with the University of Wisconsin-Madison. She holds a Bachelor of Arts in Interior Design from Mount Mary College, Milwaukee, and a Master of Architecture degree from the University of Wisconsin-Milwaukee School of Architecture and Urban Planning. She is a past vice chair of the AIA National Disaster Assistance Committee and current co-chair of the AIA Wisconsin State Disaster Assistance Committee. While serving on AIA Disaster Assistance Committee, Janine participated in the COVID-19 task force response efforts in 2020 to help inform designers and building owners. Janine has also worked with several NGOs on international disaster response, recovery, and resilience projects in the United States, Haiti, Nepal, and El Salvador. Ms. Glazier, thank you so much for being here. The floor is yours.
Thank you, Pooja. I'm going to share my screen. Okay. I am incredibly honored to be here and very humbled to be among the panelists that are presenting this weekend in the symposium. So I'm going to talk about another way that science can inform healthy building and space design. I'll introduce my background with disaster assistance and how the American Institute of Architects Disaster Assistance Committee used the tools created for responding to natural disasters. And we adapted that for the COVID-19 pandemic when it began in 2020. So think about how building and interior designers can develop a guide specific to interiors for mitigating viral transmission, creating healthier design, interior design for all building types and spaces. So I wanted to thank Andrea for kind of the nice segue into this presentation, sharing a little bit about what I'll be talking about. The AIA and its member architects are dedicated to the health, safety, and well-being of our communities. This is reflected in the Code of Ethics and forms the foundation for many AIA programs, including the AIA disaster assistance efforts. So our goals are to support the state disaster assistance coordinator programs. Every state across the nation has a state coordinator. And the committee also creates tools and resources. And we like, that will inform programming. And ultimately, our team, when the pandemic began, created a COVID-19 response task force and developed reoccupancy tools for reopening of public and private facilities. So I want to start by recognizing that there were a lot of people that contributed to this. I just happened to be in the wrong place at the wrong time with the right people. Serving as the vice chair on the Disaster Assistance Committee, where Scott Eddy was the chair. And there were many, many individuals that contributed to a number of white papers that were released. I also want to recognize the AIA staff at the time, Rachel Minery and Lindsay Bruger, who worked tirelessly to keep us all on task throughout the process. So I'll tell you a little bit more about how an individual, how a design professional can get involved in disaster assistance. So you must go through some disaster assistance training. And this program is called the Post-Disaster Safety Assessment Program. We refer to it as SAP, Training for Evaluators. This program was actually created by the California Office of Emergency Services. California, as we know, faces a lot of different climate disasters, from fires to earthquakes, storms, flooding, a wide array. And a certified SAP trainer, once activated, can appear on site and begin these evaluations. I've been a certified SAP trainer for over 12 years, and everyone must go through this certification program. We encourage folks not to just show up on site. So when asked how building designers can get involved with disaster assistance work, I'm usually talking about responding to natural disasters like earthquakes, fires, hurricanes, or floods that impact a community. My very first experience with disaster assistance was working with Architects Without Borders from Seattle on post-earthquake building assessments in Haiti after the 2010 earthquakes. I remember asking when we first heard about the earthquakes, there's a Doctors Without Borders helping people. There must be an Architects Without Borders. And sure enough, I found the AWB group out of Seattle that was planning a trip to Haiti to conduct post-earthquake building assessments to find structures that were safe that people could go back into. Another experience a little bit later, I found an NGO, non-government organization called Namaste Nepal. This group is actually based out of the Czech Republic, and they had very personal relationships with several villages in outlying areas outside of Kathmandu that were greatly impacted by this major earthquake. And our focus on this particular response effort was a little bit less on the safety assessments and more on the rebuilding program, creating an opportunity for local residents to learn how to build back safer using local materials and get a certificate so that once they go through the training, they can build back their own home, but also get work. So that was a pretty exciting opportunity to work with these folks in Namaste, Nepal. So I'm going to give you one more example of disaster assistance, just to help you understand how we broach a natural disaster and then how we adapt it for design and responding to a pandemic. So this is an example a little bit closer to home from my Wisconsin city of Madison. On Tuesday, August 21st, 2018, a torrential rain event swamped Dane County and the Madison area, causing widespread flooding, washing out state highways, stranding people in their cars. Rain fell so fast and so heavy, streets turned into rivers and parking lots. Playgrounds and fields became lakes, and the governor declared a state of emergency in the county. So, in partnership with AIA Wisconsin, Wisconsin Emergency Management officially activated us to respond to the situation. We worked very closely with Dane County Emergency Management and the local municipalities to collect this data, do post-flood building assessments. What does it look like? And why architects or designers? Why are architects valuable partners in responding to and recovering from disasters? We're trained experts. We go through architectural training, licensure, and experience that give architects a sound understanding of building safety and building code principles. Disaster ready. Locally and across the nation, we've made the commitment to become trained for effective support of local disaster planning, response, and recovery efforts. So project leaders, architects are also experienced at working as part of a collaborative multidisciplinary team. We've heard that a lot in previous presentations, that it's this cross-section of people from different disciplines coming together and bringing and sharing information. So critical. Architects are also citizen leaders whose license comes with the obligation to protect health, safety, and well-being of the public. So as you probably know, one of the first tasks for a community struck by a disaster is to determine whether the buildings are a public safety concern and are safe for reoccupancy so that people can start rebuilding their lives. The trouble is the structures that must be examined often greatly outnumber the quantity of trained city inspectors. And if you think about a worldwide pandemic, we know that the number of structures outnumbered those available to do the safety assessments for reoccupancy. So architects, we spend a lot of time on construction sites. So we're used to going out into the field. We grab our clipboard, we love checklists, and put on our safety vest, sometimes a hard hat, and we go out into the field. And we conduct a safety assessment by walking around the building. And we're collaborating very closely with other people. And we're collecting data on what we can see. That's the key. You can see if structure's damaged, and you can fill out your checklist and assess the level of damage. So let's take a step back. The phases of disaster assistance include response and recovery. So I was just talking a lot about response and recovery, but it also includes mitigation preparedness. So I've been talking about response and recovery. So doing safety building assessments and helping a community rebuild after a natural disaster. But when it came to responding to a pandemic, I think we're looking at the left side of the screen a little bit more, focusing on preparedness, vulnerability assessments. How vulnerable is this building? How vulnerable are the occupants? And how vulnerable is this community? We're also looking at mitigation. How can we retrofit an existing building? But also, how can we think differently about designing new buildings? So architects and interior designers can work together to create resilient communities. By using sustainable design practices, materials, and techniques, architects and designers are uniquely poised to provide solutions to create healthy buildings and spaces. So this AIA multidisciplinary team conducted a virtual charrette workshop. We love charrettes. And this was a method used to study specific issues in a limited time frame in an intense brainstorming session. And our goal was to develop strategies that reduce the risk of virus transmission in buildings. Using the AIA reoccupancy assessment tool framework, the team identified virus transmission hazards, characterized risk in buildings, and developed strategies, we'll call them controls, to minimize those risks. Keeping in mind that there weren't just architects on these teams, there were many medical and public health experts that contributed to a lot of the decisions and the development of these tools. So successful strategies reduce the spread of pathogens, accommodate physical distancing guidance, promote mental well-being, and otherwise meet the demands of pandemic-informed new day-to-day lifestyle norm. Strategies range from temporary to permanent. So this 33-page assessment tool used the CDC, Center for Disease Control Framework, hierarchy of controls. Andrea talked about this in her presentation, with the goal to select ways of controlling workplace hazards. The AIA reoccupancy assessment tool is a list of considerations that includes engineering controls, administrative controls, as well as PPE that apply to essential business operating under current restrictive orders and for closed non-essential facilities that are in the process of reopening. The intent of this assessment tool is to provide steps that reduce the risk of occupant exposure to SARS-CoV-2, the virus that causes COVID-19. Events of the pandemic transformed the way we work, the way we learn, and the way we live. I mentioned that there are multiple documents and white papers that were developed by the AIA COVID-19 task force. But the one most relevant for use today and for the future is this reoccupancy assessment tool, version 3.0. Now, it's helpful to use some of the partner documents with it that were very specific to individual building types, including schools, offices, and senior living communities. So before you start the checklist, let's take a look at what the baseline parameters are. Number one, identify the team. It's ideal if there are multidisciplinary team members, including an architect, quite possibly an engineer. Absolutely must include the building owner, the facility manager, and quite possibly an occupant of the space. because we're all going to be looking at it from different perspectives. Additionally, the team must be committed to the same goal of reopening safely. The team must have the authority to make these decisions. That's pretty critical, because without that buy-in, you're not going to get very far. You must have permission to conduct this assessment. So if the intended operation of the facility cannot meet these baseline parameters, the facility is likely not a good candidate for following reopening considerations for minimizing the risk of spreading SARS-CoV-2. Also, the facility may have additional prerequisites considering what type of facility it is. Did I mention that architects like checklists? So the checklist on the left is a form we use to determine which buildings were safe to go back into following earthquakes in Haiti. It's called an ATC Applied Technology 20 Safety Assessment form, with an area where you can fill in building type, you can check boxes on the level of damage, and there's also an area where you can add notes. Now, these are buildings where we could see the level of damage. We could easily walk around and fill in the form. What happens when you can't see the danger with your eyes? Well, a lot of the scientists that I've been speaking yesterday and today, I've been talking about just that. So with the checklist that was created on the right is a form to determine which buildings we're safe to go back into, much like the other one. How can we go back into a building and make sure it's safe? This is page 8 from the Reoccupancy Assessment Tool, version 3.0. It's laid out with some symbols, some check boxes, and it's all organized to guide the person filling out the form to determine which would work best for their building or space type. So not all controls may be applicable to all building types under all situations. Similarly, I mentioned additional controls may be necessary. So the image on the left shows a list of the different building types that were considered: education, office, restaurant, senior living, retail, and housing. And you see a symbol with a letter in it. Each symbol has a different color. And on the image on the right, you can see some of these symbols peppered across the form. And that's to give you a hint that that particular control or approach might be better suited for that building type. And additionally, your ultimate goal is to prioritize these. Which ones are essential and which ones are desirable? The assessment tool does not prescribe required solutions, but applies controls to many building types and scales of operation. Building owners are encouraged to communicate their mitigation measures to the occupants to foster transparency that could help the public make informed decisions about their own health and safety, and maybe the health and safety of others. The architectural and engineering features include spatial, finishes, furniture, partitions, additions, facilities, mechanical, systems, plumbing, and electrical. For today's discussion, I'll focus on 3 of these areas that might be a little bit more relevant to interior designers and other types of designers. These 3 areas include programming and space planning, mechanical and passive ventilation. We know that that's a critical approach, and finishes and furnishings. So starting out with programming and space planning. Again, consider which design controls are essential and which are desirable. Think about this particular image. This shows what was once a double classroom space turned into a single classroom. Again, early on in the pandemic, we used the information that we had to make some decisions. Utilize this large interior space as an extended instructional space. Additionally, in the upper left-hand corner, you can see outdoor spaces. Provide outdoor spaces for learning and working. And then utilize a parking lot for waiting areas. There's a lot of opportunity to think differently about how we use space. Taking a closer look at programming and space planning for a classroom environment, here are a few reoccupancy tool controls that set the standards were returning to schools early in the pandemic. We talked about staggering the placement of furniture, perhaps mapping the floor to identify where the instructor is and where the students are, and provide a locking mechanism on chairs and tables to hold them in place, but also make them flexible to move around, and also provide virtual learning. Which of these tools and controls, if any, do we want to use to reimagine and design schools and offices of the future? I have some examples. Biophilic design is a design approach that seeks to connect building occupants more closely with nature. Biophilic design buildings incorporate things like natural lighting, ventilation, natural landscape features, and other elements for creating a more productive and healthy built environment for people. Use nature as your guide. We know now more than ever how important it is to prioritize mental health and wellness in interior spaces. Here's an example from University of Wisconsin-Madison. Provide conferencing and shareware software to facilitate remote learning and collaboration. Hybrid meeting capacity. This is actually a room model where many students and colleagues may work remote while some are in the building on alternate days. Provide a spacious, well-ventilated room with large digital monitors that also have a kit with the camera and speaker. You can use low-tech or high-tech equipment, and we are continuing to update more UW-Madison classrooms and meeting rooms with this technology. Another example for providing options for in-person and virtual student collaboration. Here's an example from the Wisconsin School of Business, where students can collaborate at a shared table or in a shared room with hybrid meeting technology. We are now reimagining how students can work and study because of what we learned in the pandemic. Transitioning to mechanical and passive ventilation. Here's an open office example that starts to think about safe HVAC, heating, ventilating, air conditioning considerations. We know that we need to monitor relative humidity, temperature, and CO2 levels because they impact productivity. Increased ventilation rates and air changes. And early on in the pandemic, we talked about cleaning the HVAC intakes daily, but at least come up with process and maximize flexibility, create different seating options. I'm not a mechanical engineering expert, and we don't expect every interior designer to be an expert. But we're hoping that with this symposium, we're empowering you with the information to ask good questions. Raise the topics in conversation because you're more than likely going to be working in a multidisciplinary team. So here's an open office example showing a shared workspace, a shared break room. One option is, again, prioritize fresh air supply. Perhaps install a retrofit and install a HEPA or MER 14 filter. And consider portable room air cleaners. And also consider installing ultraviolet germicidal irradiation and mechanical vent paths. Here's an example of a student study space that we're looking to optimize flexibility and create multiple seating types and varying layouts within an open, well-ventilated space. Here's another example of a shared eating facility. And again, I'm transitioning from mechanical and ventilation to finishes and furnishing. Looking at how this shared eating space could be used and thought about differently. We talked a lot about ventilation, but what about the layout? What about the fixtures and finishes within the space? Number one, start by removing non-essential furniture and equipment, maximize flexibility. Think about the furniture. Provide wheels on the chairs, wheels on the tables. You can easily move and adapt them based on perhaps the flu season or the use of the space. And then perhaps maybe provide a flip-up table so they can easily be stored in another area and then brought out and set up. Also, provide touchless hand washing stations and touchless trash cans. And I know that interior designers are going to be specifying this equipment. And kind of wrapping up a little bit of my conversation on, how can we carry this forward? Here's an example of a floor plan layout of a new office that we're proposing on the UW campus, whereas within an office space, and they've requested different ways to work. The seating on the right represents some soft, comfortable, casual seating with flip-up tables. The area in the center represents a booth seating option, and the area on the left represents an individual workstation that is adapted for sit-stand, but also is movable. And this is what that workstation would look like. This is the model we're starting to incorporate more and more throughout different offices on campus, something that provides privacy, but also could be moved around if we needed to think about different hazards. So we think about the future of design. How can we use this information to create healthier buildings and spaces? We still have a lot to learn, and we can still do better, but we can take what we learned from this symposium and maybe start with bathrooms. We've talked a lot about bathrooms and the opportunities. Continue specifying touchless fixtures. Continue thinking about airflow, perhaps creating a layout without doors to maximize air circulation. And I'm sorry, but I'm going to bring it up. Let's talk about those toilet seats. It's something that you can easily specify to help minimize some of that hazard in the space. I'm going to end by saying that the American Institute of Architects would like to recognize the expertise, time, and significant effort of the AIA 2020 Disaster Assistance Committee and the AIA COVID-19 charrette participants in cultivating this tool. It took many experts to bring this together. So as myself as the vice chair, Scott Eddy at the chair, AIA staff, Lindsay Bruger and Rachel Minery, who were critical in keeping us on task, and of course our peer reviewers, a lot of which had medical and public health backgrounds. And then we had the project team. And I wanted to say that we did ultimately dedicate this tool to a member of our team who we did unfortunately lose to COVID-19 last year, Mo. He's from California and a longtime advocate for disaster assistance and how architects can help communities become more resilient. So we dedicate this to him. So with that, I'd like to hand it back to Pooja for questions. And I'd like to thank you again for inviting me to participate in this symposium. And I'll see if I can figure out how to stop sharing.
That was fantastic, Ms. Glazier. Thank you so much for sharing all of your incredible life work in disaster assistance with us. And it's incredibly interesting how the principles and approach to disaster assistance has been translated to the development of this pre-occupancy assessment tool. It especially speaks to how the learnings from these related disciplines or problem types can translate to the ones, which is kind of the theme of our symposium. And all of the visual examples were also really helpful to us designers, I'm sure, to see how the tool can be translated to design solutions. Let's go to the Q&A now. We have a comment from the audience, not necessarily a question, but a comment. I remember hearing an orthopedic surgeon complaining about the number of people circulating in the operating room and how his surgical rate of infection had gone up since moving to this new hospital. I now better understand that resuspension may have been a contributor. So a special thank you to Dr. Ferro for the presentation.
Thank you. I do want to mention that some of the earliest resuspension work in the 1950s was from operating rooms. So in that case, the clothing should be clean, but there's still resuspension from surfaces.
Right. Right. So maybe we'll stay with you, Dr. Ferro. I do have a question. Looking at all of your studies, you have done research on flooring materials, looked at clothing, and just resuspension on surfaces in general within a space. In the sessions yesterday, my key takeaways was for healthy interiors at a high level was improved ventilation, air filtration, UV technology. And then with this session and the last session, we've looked at resuspension. With the last session, we looked at targeted hygiene and cleaning protocols. So with resuspension now, there is an added consideration around choice of materials. And I think with, looking at it from a interior design perspective, it's particularly around choice of flooring, countertops, wall surfaces, those types of materials. So based on your research so far, we saw your research around flooring materials. You mentioned that vinyl and hardwood flooring are preferred over carpet, whether it's high or low density, just given that it in terms of resuspension, it reduces the number of particles that resuspend into the air in layman's terms. Forgive me if I don't use the proper terminology. I'm curious about whether you have explored anything around floor tiles, ceramic or stone, and what the outcomes have been with that.
Thank you for the question. I think that just sort of going back to those, using ventilation and filtration and germicidal UV, these are all good approaches, even thinking about resuspension as the source, right? So it's a way to get those particles in the air. Some of them may be infectious, and so it's effective to use those. I've not looked at ceramic, but my expectation is that it would be very similar to the hardwood and the vinyl. So it really has a lot to do with the roughness. And Dr. Lee talked about surface roughness in his discussion about how, there's transfer of material to hands. Surface roughness makes a big difference in resuspension as well. And depending on the level of roughness. So we have excellent models that have predicted sort of what force it takes to detach a particle from a surface, incorporating that roughness. So I would expect it to be very similar to the other hard surfaces. There's also issues with electrostatic. So I'm getting in the weeds a little bit here, but different types of surfaces would have tend to build up electrostatic effects that could, also impact that particle detachment. So, but again, I think that, you would get a similar result, but I don't know anyone who's looked at tile in particular. I mean, ceramic, yes.
Well, you spoke about rough surfaces. Just for my understanding, does that mean that the smoother the surface, the less the resuspension, or is it the other way around?
Yeah, it depends. It depends on the size of the particle and the size of the roughness. So there's sort of this, it's not a linear relationship, but in general, you can think about if a particle's sitting on a surface with that's very rough, then the amount of contact area of that particle on the surface decreases. Therefore, your mostly van der Waals forces that are keeping that particle on the surface have decreased. So it's mostly that the higher roughness would increase the resuspension, but if depending on the size, again, there could be particles that get caught in those in the surface roughness, and then it sort of goes the other way. But
right. I was curious also, I'm not sure if you've done any studies on this, but for counter surfaces, looking at, a solid surface versus a stainless steel surface versus marble or engineered stone like quartz. Have there been any studies done around that? In my mind, I'm thinking about the porosity of certain materials, and how they may kind of hold certain, I guess, certain droplets in there. Is there any sort of work done around looking at counter surfaces?
No, but I think one thing about counter surfaces, you need a pretty large force to detach those particles, right? You can think about dropping some books on a counter and you're going to see, you probably see the plume, right, of particles in the shaft of sunlight, possibly. But so some activities that we would do on counters would resuspend particles. Others might be, maybe the transfer to the hands would be more important. That's true for seating, you know, for couches that are soft. If you sit on the couch, the particles are going to effectively move from the couch into the air. So I think it has to do with the human activity, that interaction of the human with the surfaces that makes a big impact. And that's something that Dr. Lee touched on as well. So I think that for interior spaces, the most important things that we should think about are where you have quite, you know, the flooring surfaces, because a person's walking on them and they're squeezing the flow under their feet, which detaches the particles, and seating. You have other things, right? You don't always want to sit on hard benches. So you have to think about, you know, the use, of course, as well.
I mean, related to that, you know, given all of the themes that have come up around increased ventilation, filtration, and even with harder flooring surfaces from this session, you know, I think as a designer, it would be prudent to also consider acoustics as a factor in this, just given that a lot of these surfaces are hard or loud or noisy devices that we're using in the spaces. And, you know, given that designers consider everything holistically, acoustics is certainly a factor to incorporate in the design of these spaces.
That's true. I mean, acoustics can be, you know better than me, but acoustics can be handled with different approaches, right? So it's still possible to have good, you know, desirable acoustics with hard floorings, but you'd have to balance other ways. I just think, you know, the combination of it being easier to resuspend off carpets and having more particles on the, you know, the carpets really trap the particles in the reservoir build. So I think that it's a good, at least for high places where there's a lot of traffic, then you certainly want to consider this.
Absolutely. Thank you, Dr. Farrell.
Thank you.
Do you mind if I add a comment to that?
Yeah, absolutely. Absolutely.
I found it super fascinating in Andrea's research when I talked about, you know, the different surfaces. We talked about one extreme from the hard surface to the carpet. Well, what about in between? And I was surprised by the tight loop carpet versus the cut pile carpet. I can't remember the last time we specified the cut pile. And you know, you're thinking about high traffic areas, you're probably going to do the tight loop or a hard surface, and how that science really informs that and supports it.
Thank you so much for that. Janine, actually, we have a comment here, just a consideration from Lois, actually, that you brought up a great point about how different disasters such as earthquakes have visible damage, and, you know, COVID has an invisible damage. And, you know, it would be interesting if you could talk about some of the discussions that took place in your team about this change or in understanding between visible and invisible disasters, let's say. And was it the first time that your team had to address an invisible disaster?
Good questions. So in short, yes, at least in my experience and what I know of our team, this was the first time that we had to respond to something we couldn't see. We couldn't, well, we could touch it, but not really. And we're visual people. Designers are typically visual. We want to see it. We want it to be pretty. We want it to be attractive and useful. And coming at this from a different tack, and we needed some experts to help us change the way we're thinking. And there was one particular individual who was an architect, but also a doctor and had a background in public health, who really helped us kind of turn the ship around and look at it and approach it from a different direction. So I'd say that was the key. someone who could break down the science into something that we could, as designers, could think about and process and use to create this tool. Does that answer your question?
Yeah, and that's a great testament to, multidisciplinary work. And I think I just want to probe a little bit more into the reoccupancy assessment tool. Some of the common themes that came up in your presentation that I kind of identified was flexibility in spaces, but also choice for the users, adaptability over time, and an acknowledgement of hybrid working models, in a lot of the guidance that you have provided. I will share the link to the tool. It is public and available to everybody. In fact, I'll do that right now.
Yes, please share widely. And
I
for
just-
those who are listening, share it with more of your colleagues.
Well, speaking of that, I mean, I'm curious to know, so the examples that you presented were predominantly in the University of Wisconsin campus. Are there any other examples that you have of, its use across the states, perhaps even in Canada? What has been the response to this tool? And are there any considerations that you have for future updates? What could that look like?
More great questions. And so
That's too many questions, I guess. I would say, okay, are there any other examples? First, I'll lead with that. Of its use. How has it been responded to, around the world, especially in North America?
Well, first off, it got me an invitation to Toronto and to be part of this symposium, which is much, much more than we ever expected. And it's been shared internationally with other folks who have used it and adapted it for their use, whether it's a university or a building owner, that we encourage, not just designers to be looking at this and using it as a tool. Facility managers. You've heard other scientists refer to the important role of facility managers in thinking about how the buildings are used and how they're maintained, how the air is circulated. So yes, I think there's a lot of examples and I'm hearing more. Is there an opportunity to adapt it for a future tool? Absolutely. I hope this speaks to that kind of disaster cycle, that image that I shared that talks about the different phases of disaster. We're still in preparedness and mitigation, and now is when we need to be having these conversations, not when the city closes down for a pandemic and we're like, what's next? How do we solve this problem? Let's think about it beforehand and start to plan. So I'm super excited that this symposium was put together to do exactly that. So thank you.
Thank you, Janine. Do we have any other questions? Let me just see. Give me a moment. Well, it seems like a quiet audience before lunchtime. So I think we'll end the session a little bit early, 5 minutes ahead of schedule. I just want to thank Ms. Glazier and Dr. Ferro once again, for sharing all of your insights with us and helping us interior designers gain new language, new terminology, better ways of thinking, and the tools to create healthier interiors. So with that, this closes session 4 of the symposium. We're going to take a break of about 15 minutes till 1 p.m. For lunch, and then return for sessions 5 and 6. Thank you so much for joining, and we'll see you soon.